Hi everybody, my name is Pak. As Brian mentioned, I work on a lot of applications for HPC Advisory Council, a lot of the HPC applications. So in this session, I'm going to mention to you, describe to you some of the findings that I worked on for a couple of the HPC applications that are well known here. We're going to go over that. As Brian mentioned earlier, so there are 130 plus HPC applications that we have done in the past. So there's supposed to be a URL way down the back, way down here, so you can actually find it on our webpage. So if you're actually very curious as to know about all these applications that are listed here, plus more, you can go to the URL actually supposed to be right down here. So there are many different types of HPC applications that are used in CFD, weather simulations and in molecular dynamics applications and simulations and other types of applications that are well known. So this is just a snapshot of many ones of them here. So the agenda for this session, first of all, I'm going to go over some of the overview of the performance and what to look for when tuning the user applications, and then I'm also going to describe to you some of the tools that I've tried before. Hopefully, you can you already know some of them, and you may discover a little bit more. And then I'm going to describe to you some of the system configuration that I use for the couple of the user application benchmarks that I work on here. So STAR-CCM is made by CD Adapco. It's going to be described later on as one of the user applications. The second one is called ANSYS Fluent, which is another CFD application that is pretty well known. And then I use those two cases as to see what you can do to maximize the performance on your job, on your HPC job. And I'm going to bring you the conclusion a little bit later on. So in order to get pretty good user application performance, HPC applications, so you first, in my opinion, you first have to kind of understand the type of workload that you're facing. So the first thing to do, at least for me, it will be to kind of find out if it's really you spend the most time in the CPU side, or the network side, or file I/O. So by understanding which part of it is actually taking the most time, you probably would get a sense of tuning one part of the parameter actually gets you the most bang of the buck, so most benefit, right? So by doing an application profile, you actually get to understand the percentage of time actually spent either on the CPU side or the network side or the file I/O side. So this is actually, in my opinion, is actually one of the things that you should watch out for. You also kind of once you understand what part of the component that you can benefit the most from. So let's say if it's a CPU that actually taking the most time, right? So you actually would start to see different by switching to a different frequency CPU or a lower frequency of a CPU, or enabling some other ways in the CPU or compiler that will actually give you the performance difference. So you actually would by changing the different hardware, this actually will give you the difference, and then from there you can predict on and to understand how much of the improvement that you're expecting. Right. So, and then in one of the implicit requirements is that each node of the cluster needs to be performed similarly. So I've seen many cases that I have users asking, how come I'm not getting a good performance out of my cluster? Then you realize that there's one of the nodes actually in the cluster actually not performing, that actually slows down the rest as you expect. So similar to a previous session from DDN, if you have one of the drives actually misbehaving, or one of the partitions actually misbehaving, it's actually going to slow down the performance of the I/O overall. So this is something implicit, but this is really important in my opinion. So there are CPU memory network an I/O test that you can actually use to check for those. And I can show you actually on a subsequent slide. As mentioned earlier, I'll bring you to a couple of user applications just to show, so you can demonstrate, the effectiveness of, doing profiling and to understand what type of the communication patterns and, and CPU utilization of an application. So you can it actually helps, explaining some of the behavior that I see by switching to different components. So, as I mentioned earlier, so some of the user tools that you can try. So I'm listing out just a few of them here. So top, HTOP, perf top, on the CPU side, so you can understand if it's the process actually binding to the right core. So HTOP actually give you that. pstack shows you the stack of it. So in case sometimes you run into code that it seems like it's hanging, you don't know what's going on, so you definitely can try that, so you can see the stack trace of the code without having to get to create a core dump of the user application. So HPAL is a good user benchmark tool that gives you the performance of the node, so that you make sure that each one of the nodes actually performs similarly before you can run your application. So briefly on the file IO side, IOStat, collect L and -n, those are the tests that you can do. On the network side, we have the perf query for the InfiniBand, and then we can also work on the IPM tool is the profiler that I actually use quite often. It shows a lot, and then of the message size actually being passed around. When you're running on your HPC application, that the IPM tool doesn't require recompiling, relinking, so we actually make it very easy to use and generate really nice reports. So in my opinion, so Tau is actually another open source tool that you can use for profiling MPI communications. So one of the case study that I'm going to show is the STAR-CCM Plus. The STAR-CCM Plus is pretty well-known CFD tool, CFD simulation software that's developed by the CD Adapco. So I'm going to use that to show, and with the workload to show by changing and comparing different hardware components, you get different results, and then by doing that, we can see how sensitive of changing those hardware to the performance. Then you realize that the benefits from using that hardware compared to some of the other ones. So test configuration that I'm using is described here. So we are using a Dell PowerEdge R720 XD cluster that is running the Ivory Bridge 10-core CPU. Has 64 gig of memory per node, and then it's running the Red Hat Enterprise, Mellanox InfiniBand OFED driver, and then it's also Intel cluster ready certified cluster, and then I listed the InfiniBand adapter and switches and the MPI software that I use. So the platform and the Intel MPI are the vendor provided MPIs. So it comes with the STAR-CCM software. So there's something called the Mellanox HPCX software that is actually based on OpenMPI that I use. I'm going to show you the differences between among the MPI that are actually being tested here. The benchmark code that I work on right now for this one is a race car's aerodynamics simulation. So it's listed here. It's the Le Mans Poly 17 million case. The first comparison that I actually work on is the comparing against different network interconnect. So by doing that, you actually can see how well how sensitive is the network interconnect is how important is the network connect is to the performance of the user application. So if you're actually working on a small number of nodes, 1, 2, and 4 nodes, so it doesn't really show much difference. So, but if you scale out to more and more systems, the system the performance difference will be more apparent, right? So, so from one node and two node, you have like 20 cores per node running on each node. So by the time you get to 32 nodes, you have 640 CPU cores running. So the amount of actually of the traffic that's generated by the CPU cores actually would be getting more and more as the number of nodes actually growing up. So the benefit of using InfiniBand is actually that you will reduce the amount of network overhead, so that it actually helps that as you scale out, you are able to maintain that scalability. So it will continue to scale. I think if beyond the 32 node and then up, compared to other interconnect that's been shown here. So we see quite a sizable increase, from InfiniBand compared to other interconnecting that's been tested. The reason for that is that, as we can see, is that the time actually spent on the MPI communication is actually less by using InfiniBand compared to other kind of interconnect, such as like 10 gigabit Ethernet and 40 gigabit Ethernet here. So the red part is the amount of time that's spent on the communication in MPI. So approximately about like 73% to around or more than that, is actually spent on communication compared to InfiniBand. So from this, it actually explains why InfiniBand is actually a lot more suitable for network communication in HPC applications, because it actually reduces a lot of overhead for communicating. So the rest of the time actually saved by communication is actually spent on the computation. So more times actually can be saved, and to work on by the user application. So this is good to point out. So this graph shows us that this is the MPI profile, by the way. So it shows it profiles the amount of communication that the MPI communication time actually spends on this input data for STAR-CCM. So what's comparing against here, maybe it's actually not showing way down here, is that you have 3 different bars. So that part of the graph is actually getting cut off. So I'm comparing again the 10 gigabit, which is the purple line here, and the green one, which is the 40 gigabit, and FDR InfiniBand is the blue line down here. So here you actually can see another difference. So what you have here is that you have the MPI receive, which is the point-to-point communication. That takes a lot more time for the 10 gig E. Similarly, a lot more time on 40 gig E, but a lot less time on the FDR InfiniBand. So MPI receive is purely just bandwidth sensitive communication method. So from here you can actually see that this is like from difference between 10, 40, and FDR, which is 56 difference. So in bandwidth. So and then it's a huge difference here. The amount of time that you save from using FDR is quite a lot compared to something like Ethernet as you scale out to 32 nodes. So for this case, 32 nodes or 640 cores are actually being used. And then you have the wait-all communication, wait-any communication, which is for waiting for the non-blocking communications to complete at some point. So right here. So that actually also would benefit a lot from using the InfiniBand part of it. And then you have another part right here that is using the all reduce and the broadcast. So those are notoriously for the group communication that takes place. So they tend to be a lot less. The message size is actually much less than the send and receive communication. So they tend to be very, they use very small message sizes. So in these two, I would say that typically they are very latency sensitive. So similarly here, so InfiniBand actually would also benefit from the time here. This is just another representation, right, for the amount of time actually spent on communication. So 10 gig you spend a lot more time in doing something. On the InfiniBand part of it is a little different. So it shows you by reducing the number of time, your communication pattern may shift. So unfortunately, this part, the legend part of the graph is actually being cut off again. In here, we're comparing two different things. One of them is the version of the STAR-CCM software that's being used. So I took the time actually to see if there's any difference by using an older version of the STAR-CCM software versus a newer version. So surprisingly, it didn't occur to me that using a more recent version would have a huge effect on the performance. More so actually in scalability, because on the 102 node or 400 cases, you don't see much difference, but as you scale out to scale your job to more and more system and more CPU cores, the effect of the improvements actually pretty apparent. So we see up to 28% of the improvement at 640 nodes or 640 cores or 32 nodes. So by using the version 9.0, 02.005, which is the one right here, compare that to the version 8.06.005. So this somehow it has to be something related to the communication library that STAR-CCM has actually used, which I was able to find by using the profile of this. So comparing the older version versus the new version of STAR-CCM, so we see that a lot of the barrier that appears on the version 8 is no longer there for the version 9. So somehow the STAR-CCM code was modified or changed to make it even more scalable, right? That's what we have demonstrated in the last slides. The rest of the communication pattern stayed the same pretty much. So this is actually a very interesting finding. So if you intend to run STAR-CCM on a lot of machines, using a more recent version is a way to go. Okay, so in this graph, we're comparing against three different things, three different MPI implementations. So what you don't see down below is that we're comparing the one in blue that's called HPCX, which is based on OpenMPI 1.8. And then the other two that we're comparing, let me see, in blue is the Intel MPI. That works. Thanks God. Yeah, because like all my slides is going to have the legend like that. So yeah, otherwise it'll be really hard to follow. So okay, so that helps a lot. So the blue one is the Intel MPI version that comes with STAR-CCM. The red one is the platform MPI, and the blue and the green one is the HPCX, which is based on OpenMPI. So it may be a surprise to many people, but by doing comparison, there is some difference as you scale out to more and more systems. So if you intend to run STAR-CCM up to 4 nodes or maybe 8 nodes, you would not expect any dramatic difference like this, because that the communication libraries that you use do not have that much of a difference. So and as you scale out to more and more systems, the difference between communication library will start to be more apparent. So all that is because I assume that they use different ways of inside the communication libraries to do to send and receive and to do group communication. So there are algorithms that involve inside MPI that takes care of how they do communications. So the default MPI implementation that used for STAR-CCM is platform, which usually is is a pretty good MPI to use. It's pretty stable. But what we have found is that by using the something called HPCX, that is based on OpenMPI package, we're able to get much better performance. So this is something that is interesting because it seems to show better performance because of the communication library that they have a different way of implementing the send and receive and to do collective operations. So HPCX is the MPI implementation that's from Mellanox. So we're able to demonstrate that it's a sizable increase up to 21% at 32 nodes or 640 CPU cores. So another thing that I took the time to try is to use to see if there's any difference by using a single port versus a dual port. It's one of the things that I get asked sometimes because it will, there's an option to use a single port for InfiniBand versus a dual port. So for communication. So in here, a 32 node, we're able to see way more difference. Difference in between the communication improvement by using a dual port InfiniBand on the adapter compared to a single port. So the difference is only apparent when you scale out to more and more systems. So up until 8 nodes, you probably don't see much of a difference. So as you scale to more systems, somehow it improves performance. So the difference between single port and dual port is more or less just the bandwidth available, because the latency side, when I use something like the OSU latency benchmark, you don't see much difference between using a single port and dual port. But the bandwidth wise, that actually improves a lot by using dual port. So somehow this actually improves the performance on these particular applications or input data. It's also one of the mystery that sometimes enabling turbo mode or turbo boost in the Intel processor would dramatically improve performance. But to me, when I work on a few of the user applications, the improvements actually varies. So some of the user applications actually improve a lot by increasing that, by turning up that turbo boost or turbo mode in the CPU. Some of them, you get some sizable improvement, but you also, by enabling turbo boost or turbo mode, your system actually run a lot harder and also running a lot more with more power. So that's the consideration that you should think of. For this particular application I studied, I actually have not showed the power usage. But for the next one, I think I tried that, and some of the other ones I also have tried that. So more recently, because I got questioned a lot on how much or the improvement that you can see from doing so. So there's something called the MSR tool to let you to dynamically increase the CPU frequency by turning on turbo boost in the user mode or I'll say kernel mode module. So within the CPU, within the operating system, you can actually do that to enable and disabling it. You don't have to go to the BIOS to turn off and on, which is a really good time saver. So this is actually a pretty useful tool in my opinion. So anyway, so back to the comparison to see how much of the improvement, and that's what I found is that at 16 node you get 13% better with the enabling turbo mode, and at 32 node that actually get a little bit higher. So somehow enabling the higher clock frequency somehow make the job runs even faster when you have more systems. So this is actually a good observation. So so enabling turbo boost, will boost the base CPU frequency. As I mentioned earlier, it will also resulting with the higher power consumption. So this is actually another interesting thing about that I want to get to. Although not many, or it's not advisable to run your input data onto something like a temporary file system or if you know depth share memory, SHM. But if you stage your input data into the local file system or tempfs, you see how much of a difference you can get from doing them. So local drive is your spindle drives that I have on each one of the system. The tempfs here that I mentioned is actually a depth SHM in share memory, in the memory. So the difference actually does not appear to be a lot, but it gradually increases as you scale out. So this is actually an interesting observation, just to see if there's actually a difference. In my opinion, I actually did not think that there would be much of a difference by staging it onto the memory itself. But I know it's going to be faster, but it didn't occur to me that. Well, actually, what I mean is that it's actually mounting on the local file system. So you have to you on one of the nodes actually acting as the NFS server. So that may be the reason, because it actually accessing from one point, rather than 10FS. You actually stage it on each one node, so you don't have to have a central place where they all got bottlenecked. So this show you the how much of this particular input data is getting affected by the local file system or the file system in general. And of course, the best approach that I would recommend is to use something more for more production environment. It's like to use something like the parallel file system, which is more advisable compared to staging locally and onto tempfs. The reason that I'm doing it like this is to show the effect. But in a production environment, of course, I think a parallel file system is more advisable. So for me, this is just a test to see how much of the improvement that you actually can see, or how much of the percentage of the performance actually coming out from the I/O. So if you really have a bottleneck in I/O, this is what's going to show for this particular input data. And I think this may be one of the final slides for this particular user application. So for some of the things that I've talked about, right? So the components that I compare with. So I took that, and I've been working on the user applications for quite some of the applications. So so for over different generations. So starting from the Intel Westmere generation, I have a system like that. When I was working on that user application, that was the version that I used, and that's the configuration that I used. And then later on, I worked on STAR-CCM with the same data, and that's the configuration that I used. And I actually just took those data, and basically I compare among these three different configurations. I want to see how much of the improvement that I actually get by for all these times that they come up with new hardware and the new software. So Intel Westmere generation of the cluster wasn't really that, in my opinion, it wasn't really that old, but the performance improvement by using the latest one is quite a lot, right? So I'm seeing up to over 2.5 times improvement by switching to the latest generation that's using the the codename Ivy Bridge CPU. And Sandy Bridge wasn't really that old either, but with the increase of CPU clock speed and the number of cores actually available, that actually would factor into the improvement. So together we with those the clock speed and things like that. So and then the network interconnect as well, of course. So the whole hardware and then the software changes, they all factor in, and we get more than like 55% of improvement since Sandy Bridge. So I think it's pretty interesting in this way. So this is just a profiling slide on how much of the time I should spend on the communication versus computation, which I have earlier probably shown you. So from one node, you spend that much time in computation within the processes in the node. So as you scale out, that percentage actually would increase. So another slide on profiling from MPI. So this application is very heavy on the small message sizes communication, but there's still also very high one that actually shown just a little bit. So they can get up to like from 4 meg to 2 gigabyte of memory. So they're widespread, but mainly concentrated in the lower, smaller message sizes. These graphs show you if there's any communication, no imbalances that happens throughout the CPU communications. So there is some. As you can see, the communication is not even. It's just the behavior of the user applications, because sometimes for CFD, there more data actually being needed to be processed on one particular part in the mesh. So that actually is understood, but it also affects how the system or how the processes will communicate with each other. This one shows approximately how much of the of data actually being passed around the network or them across the processes between the processes in the network. So as you scale out to more and more systems, more and more data going to flood through in the network. So this is again expected, but it's about 1.5 terabyte of data actually being passed around with by the switch in the network. So it's an interesting observation. So for this particular input data. So as a summary for this application, so we see that using the latest STAR-CCM software improves performance by a huge percentage. If you tend to want to scale out to more systems, up to 32 nodes that I see 28% improvement. So which is quite a lot. So it means that if it takes like 1 day to run your simulation, you basically literally shave off 6 hours of your simulation time. So I think it's huge. So InfiniBand definitely is the way to go. And then it also compared to other interconnects. So this shows it gets you very good performance. So dual link on the of the Connect IP interconnect. As you scale to more systems, it gives you better performance for this particular application. And then we also can see that throughout all these different generations of hardware that's been used and that I have tried, their improvement from 55% compared to a Sandy Bridge configuration versus 2.6 times as much performance that you can get from by upgrading your Westmere hardware configuration. So, and Turbo Boost it improves performance by 17%. So, and then HPCX seems to improve performance as well for the MPI layer. So that's pretty much it for the STAR-CCM application. So I'm going to jump on to the ANSYS Fluent, which is also going to be a CFD application. So this is also one of the well-regarded CFD applications out there. People use it for fluid dynamics and as mentioned here, numerical analysis, math theory of the DFT. So different way of many different areas of the fluid dynamics that actually can be done with the Fluent. So this is one of the well-known CFD software out there. So similarly, I'm going to try to see how much of how sensitive are those hardware components for this particular user application, and how do I make it even more scalable for ANSYS Fluent. So similar hardware configuration that I got in, for conducting this study is a Dell PowerEdge R720XD 13-node cluster that's running Ivy Bridge. So eventually we'll upgrade this cluster, and then we'll get more studies on the newer hardware as well. So InfiniBand hardware that's used is called Connect IB, and then we're comparing against the slightly older generation of the InfiniBand hardware as well here. They're actually also running the Ethernet protocol. And then the switch that we use is mentioned here. And for ANSYS Fluent, the couple of the MPI implementation that are provided by ANSYS Fluent are the Intel and platform as well. So platform, once again, is the default MPI, but we're also going to try with something newer that's called HPCX, that's based on OpenMPI. So HPCX we'll use right here is this version, which is a little bit later version that what we have tried earlier. ANSYS Fluent 15.07 is the latest ANSYS Fluent version that's out there. I'm going to try to compare with a few of the benchmarks that are available to me. So they're pretty much can be found in the benchmark page. The description of those test cases can be found on the benchmark page by ANSYS Fluent. So again, first of all, I want to try to see how much of the improvement that you actually can get by switching to different network interconnects, right? So by switching or by trying to differentiate between network interconnect, you can actually see if there's if the hardware actually will make it more scalable or not. So for this application and for this input data, I was able to demonstrate that the latest FDR InfiniBand, that's Connect IB hardware, is able to perform much better than the QDR interconnect. So it actually improved quite a lot, quite significantly. So differentiation starting probably from 2 to 4 node, and then you continue to grow. So for my 13-node test case, and I was able to see quite a huge difference between the QDR and FDR interconnect by approximately 2 times. So, and then compared to some other ones like Ethernet base, the difference is also is by a wide margin as well. So up to 16 times better performance by using FDR than 10 gigabit Ethernet, and just for cakes I use 1 gig E to try as well. So this actually helps to understand if ANSYS Fluent is actually, or if this input data is actually very sensitive to the network performance. So this actually shows you that, because by switching to different network interconnect, it shows that FDR InfiniBand outperforms the rest of them. This is another view of the previous comparison, but there are other test problems that are given for ANSYS Fluent. You'll see some similar performance differences, throughout all these input data that they're given for benchmarking. So we try different test cases like Turbo 500K, the 2 million K. So the number is actually the 4 million. The number is actually the number of cells actually in the test in those test problems. So similar behavior actually is seen by trying different problems. So FDR InfiniBand definitely is outperforming the rest of them compared to other interconnects. So before I dive into the other areas, I actually would want to show similar to what I had before, right? So I'm trying to see if using different MPI implementation will actually make a difference, would make a huge difference. Once again, I think for this particular application, platform MPI is also the default MPIs being used. So usually it actually gives you pretty good performance out of the box. So, but I'm trying something newer that's called HPCX. So in here, we're showing very good scalability with HPCX, even better than the platform. As you can see, we're scaling out to 32 nodes, and then we're approximately getting like more than like 10% and 19% compared to the other MPI using HPCX versus other MPIs that are shown here. A few of the things I actually want to point out is that HPCX so far is not actually being supported, but ANSYS Fluent actually has support for OpenMPI, which is the support actually I'm using to make it work. So some of the flags that I'm putting to make it work are shown here. So in case anybody wanted to attempt to try it, so here it is. One thing I want to point out is that there's something right here. It's called a YALA PML. So this is a little newer PML module that comes with the HPCX. So the YALA PML appears to really reduce a lot of overheads in the communication. So it speeds up a lot of time, by switching from the older one, which is called CM, Connection Manager, I think, in the PML level. PML is the protocol management layer in OpenMPI. A few other things that I want to describe here is that these are the enabling the FCA flags. So FCA stands for Fabric Collective Acceleration. So it improves performance only for applications that use a lot of MPI collectives, such as all-reduce and barrier and things like that. So later on in some of the slides, I'm going to show you in the profile that what kind of communication pattern and why this would actually benefit the performance. So inside these flags here, this is for enabling something called MXM, which is yet again another module that comes with the HPCX package to actually enable the scalability of the performance. And eventually, I'm going to show you a slide that actually compare the best performance that are out there listed on the ANSYS Fluent webpage with my performance actually game here, just to see how far or how close that we're getting to the best numbers. So before I go there, this is another comparison among the MPI implementations. So HPCX versus platform, which is a default MPI, which we can see that there's some difference improvement, from HPCX versus the rest of them. So this is also good to show because all these test cases have different characteristics. In my opinion, I think the ones that have the larger numbers are more CPU intensive, appears to have a little bit, slightly less, communication that takes place. But however, I think it's also good to show that HPCX, has some improvement compared to the rest of them. So, as I mentioned earlier, I want to show a slide on the turbo mode. And this one, I compare enabling turbo mode without and with for two of the bars on the right. So the light blue is the one without turbo mode, and the darker blue is the one with the turbo mode. So the improvement is more like 13%. However, it translates to the power that you actually need to use is like 25%. So you do spend a lot more power in enabling that for that 13% of the performance improvement. And then if I lower the clock to 2,000 megahertz compared to 2,800, I save, I spend, I spend less power, right, by switching to a low clock frequency. However, the performance loss is actually much bigger. So in my opinion, it doesn't make sense to lower the clock, but if you have the option for doing turbo mode or not, you can consider that. I know that I don't have much time, but I'm going for probably 1 or 2 slides more. So as I mentioned to you, with these kind of tuning that I've shown you here, using HPCX and tuning flags and for MPI, I'm able to get much better performance that I actually can get out from compared to the best number that actually being published, which currently is the configuration listed right here. which is the gray XC30 Intel, which runs a really slightly higher CPU clock speed. So that's why up to 1 node and 2 node and 4 nodes, I don't see my configuration beats that one, because they obviously have an advantage, have a higher clock frequency, but the scalability of HPCX actually helps and to improve, compared to the 30 node that I have. So we're able to beat the best configuration, best submission for the ANSYS Fluent benchmark by up to 26%, 25%, sorry. So this is quite a significant improvement. So what's also listed there on the web page, on the benchmark page, is that there's a 96 node benchmark that should have been shown there. The 32 node Jupyter cluster that I use is able to beat that as well, so by 4.48%. So in case you're actually running a 96 node job, you would definitely want to try out by reducing the number of nodes by using a better way of communication, like MPI. So this is a really interesting slide. And then I think finally, I think I want to show you this is a brief I/O profiling part of it. So this is a benchmark, so it may not have that much of this I/O activities, because that actually can affect performance too. So that's why I don't see much of these activities. But imagine that when you have a real application data set, a lot of read-writes and rewrites actually would take place in the benchmark. So I think I don't have much time, but I want to point out to you that there are some sizable amount of communication that's all reduced. So that's why something like FCA package is actually going to improve the performance. So this is a summary of the things I talked about. So the latest FDR InfiniBand somehow improve performance over QDR, and then HPCX able to deliver better performance against other MPI implementation out there. And then my the submission that are listed on the ANSYS Fluent webpage, somehow the configuration that they were used with HPCX able to exceed that. So this is a really good way of showing how much of the improvement that by tuning these kind of things can improve on your application performance. So this is all I have. Thank you very much for your time.
Any questions for Pak?